Hi everyone, I'm Hanwen Jiang. I'm happy to introduce our work, Hand-Object Contact Consistency Reasoning for Human Grasp Generation. This work is done with Shaowei Liu, Jiashun Wang, and advised by Professor Xiaolong Wang. The motivation of our work is to understand how to grasp 3D objects. As we all know, grasping the object is our human's primary way to interact with the physical world. So for building embodied artificial intelligence, it is important to learn this ability as a primitive skill. There are some possible applications with human grasp generation. We can use the results for more realistic virtual reality experience and better animation. Moreover, the synthesized grasp can be a good source for robot imitation learning and enable robots to grasp and manipulate objects like humans do. For the human grasp generation task, the input will be the object point clouds. The output is a human grasp, which is parameterized by the hand manual model. As shown on the right, the output should be a reasonable grasp of the input. We know that for each object, it can be posed in the world coordinate with multiple different 6-dot poses. So the grasp will not only be determined by the object geometry, but also the object pose. There are two targets for the generated grasps. These should be physically plausible, and the hand pose should be nature as human hands. However, due to the high degree of freedom nature of the human hands, it is hard to generate perfect grasps by directly regressing the hand parameters. So, for achieving the target, our solution is reasoning the contact consistency between hand object. So what does the contact consistency mean? From the hand-centric view, the synthesized hand should contact the object surface without penetrating into it. And from the object-centric view, there are also possible contact regions on the object, commonly grasped by the humans. The regions should be touched by the grasp. Moreover, a good thing of contact consistency reasoning is that it can work on out-of-domain objects effectively and improve the generalization ability of the model. It is possible to refine the generated grasps under the consistency. Details will be covered later. So in this paper, we reason the consistency from two aspects, as the framework design and the loss function design. We proposed two networks in the paper. The first is called grasp CVE, which is a generative network aiming at generating grasps. In the training, the inputs will be the both hand and object, and we train both of the encoder and decoder of the grasp CVE. The loss function will be introduced later. At test time, the input will only be the object, and we only use the decoder of the grasp CVE to generate human grasps. The second network is the deterministic contact net, which is used for predicting the object contact map. The contact map are scores defined on each object point, illustrating the possibility to be touched by the hand. The input of the contact net is both the hand and the object. In training, we train the two networks separately on ground truth data. Thus, the two networks are parallel in training and will not influence each other. In testing, we proposed a test-time adaptation method for refining the initially generated grasps. We unify the two networks in a cascade manner, and the contact net provides self-supervision signals. We first generate an initial grasp. Then we forward the initial grasp and the object into contact net to predict a target object contact map. Then we can reason the contact consistency between the two outputs. If the grasp is good enough, the two outputs should be consistent, which means the hand should grasp on the regions on object with high contact scores. We use the consistency as a self-supervised loss. There are also some discussions in the paper on why the prediction of contact net can be used as a target. Then we learn from the loss for several iterations. By learning, we do not directly optimize the hand parameters, but optimize the parameters of the grasp CVE. In this way, TTA can better leverage the model parameters trained on large-scale datasets as a prior. In the end, we get the final grasp. Also, for training the grasp CVE, we propose two novel loss functions. The first is an object-centric loss, which ensures the object common contact regions of ground truth to be touched, but does not specify which finger or hand part should contact it. And then, a hand-centric loss finds the answer dynamically by encouraging the hand touching object surface. We use three datasets in the paper. We train a model on all-man training set. we not only test on augment test set and also test extensively on out-of-domain HO3D and FPGA datasets, where the objects are different from augment. First, we show examples of generated grasps for both in-domain and out-of-domain objects. Here are two examples on in-domain objects. You can see the grasps are both physically plausible and have natural human hand poses. Here are some more results. And also two examples for out-of-domain objects. And more results. Please check the supplementary of paper for more visualization. We also visualize the process of test time adaptation. So before the TTA, the hand penetrates into the object in this sample. At iteration 2, the penetration decreases. Also the same for iteration 5. At iteration 8, the hand is repelled out of the object. And finally, it becomes closer to object surface. Here is a comparison between the initial and final grasps before and after the TTA. Also, from the view of objects, the contact regions become larger after TTA, which implies the grasps can be more stable. For each canonical object, by changing the object pose and sampling multiple random latent codes, we can generate diverse grasps. For evaluation, we mainly use 4 metrics. They are the penetration between hand object, the grasp displacement in the simulation, the perceptual score, and the contact measurements. Specifically, in the simulation, the object displacement is calculated for measuring the stability of grasps. Ideal grasps should have smaller object displacement. In general, larger penetration will lead to smaller displacement, and the model should find a good balance between them. First, we show the results on the in-domain augment test set. Our method outperforms the previous SOTA grasping field for all metrics, and even better than the ground truth in some of them. For the out-of-domain HO3D dataset, our method even achieved better results than the ground truth and the grasping field in all metrics. Note that the ground truth of HO3D dataset is calculated from multi-view images, and the hand may not have ideal contact with the objects. Generally, this shows the good generalization ability of our method. We plot figures for showing the balance between grasp displacement and penetration on the 3 dataset. The point closer to 0 is better. As the figure shows, after aiding TTA, the point moved vertically from the green to red. This means our model achieved better simulation displacement, or say the grasps are more stable without sacrificing the penetration volume. We further compare the learning-based TTA with the optimization-based one. The optimization means that we fix the network parameters and directly optimize the hand parameter. The TTA means we optimize the network parameters by learning. The offline TTA reinitiates the model parameters as a pretrain for each test sample, and the online TTA reinitiates the model parameter for multiple test samples. The optimization target or loss functions are the same for all of them. As shown in the table, both optimization and learning-based TTA can improve the performance, and the online version of TTA, which can continually learn on new test samples, achieves much better performance. Thus, it is effective to use the network parameters as a pry. In conclusion, we reason the contact consistency between hand-object in both training and testing for more realistic and generalizable human grasp generation. Thanks for listening.